The next speaker is Simon Eiden, working for Tech for Fuels, and he has been working for OVI, a German research institution for fuels, for a long time. And since 2018, he's been a manager of business unit testing at Tech for Fuels.
Good morning or good day to everybody here from Aachen, from Germany, close to the Netherlands and Belgium. Also, thanks for the possibility to have a talk today. I think in the last two sessions, and of course today, we heard a lot of the need for alternative fuels and the challenges behind that topic. And in this presentation, I would like to focus on the performance of the fuel itself. If you take a look on our overall goals, it will always be the significant and fast reduction of the greenhouse gases. And I think there are various approaches which can lead to a reduction. But I think at this time we need a really fast and significant reduction. And one of the fastest approaches, I think it's the introduction of renewable or alternative fuels. So the liquids, synthetics or bio-based fuels. And maybe in combination as a hybrid system. I think another approach is the efficiency of the system. So it's always a new technology or development step which is done here. So in this talk, I would like to focus or make some lead questions about the fuel quality and the performance itself. So maybe we have some topics which can be done with an additive treatment. I would like to focus this also in this talks. But first of all, a little bit more general approach. New fuels or before market introduction have to be fit for purpose. And what this means, I will show you on the next slides. If I change now the point of view as a manufacturer or chemist or biotechnique, and I've created the most brilliant fuel ever, which is CO2 neutral, less consumption and no soot formation during combustion, and I know it's really good, but I'm pretty sure I shouldn't give it in the market before testing if I want the acceptance of the client, maybe. So before market introduction, new fuels should be tested. So first of all, the interaction of materials, fuels and components, at least the first step. Because I want a wide range of clients. So if my fuel is only working in new systems, maybe it's not so good. So a second step, check of combustion behavior, also the long-term testing in the lab, and last but not least, the field test in model regions. So is it working in the field or not? The fuel material interaction can be tested in various ways, depending on the effect you want to look at. So I would like to give you an overview about some static compatibility tests. So we see here on the right side some storage of elastomers or metal plates or metal components of the whole system in order to check for the operational safety. So do we have a swelling or corrosion on the material? Here in the storage. On the left side, we see the fuel aging itself. So it's a long-term stability test at different temperatures. Here's an example with glass bottles with and without copper coil as a catalyst. And that's a kind of accelerated test in order to build up the aging in the tank of the customer. As an example, I would like to show you some pictures of such a long-term storage in the glass bottles. Instead of all the analytical data we measured during the storage, I would like to show you just the bottom of the glass bottles. And we have here 2 time periods, 12 and 18 months, and some different fuels tested. So starting with the B0, it's a domestic heating oil, fossil-based. It shows a quite good performance with no deposit formation. And if we add then some fatty acid methyl esters, 10% or 20%, B10, B20, we saw a huge amount of deposits during the storage. And this can be avoided with additive treatment. Here we saw on the right side 12 months and 18 months with no deposit formation. But the point of this slide is I would like to mention that all these analysis we did during the storage, or if we have a standard analytic in the lab, none of them are focusing or including the deposit formation. So if we have a sampling in the customer's tank, we will never sample the deposit formation for standard characterization of the fuel. But it's one of the most important issue if we have this deposit formation afterwards in the system. And this should be the point of this task slide. So the second step after the lab test was the combustion test or combustion behavior. So we did already some tests in this field here as an example with the domestic heating oil and some hydrogenated vegetable oils, H100. And parallel to the combustion behavior tests, we also had the long-term storage. And we saw here in all the pure fuels, as well as in the blends, no significant change in the physical-chemical characteristics. But if we then tested them in the burner system, so we saw it here in the, or see it here in the slide, the both pure components show nearly no deposit formation or any malfunctions in the system. But if we take a look in the first line, we saw the ISO H15, so it's a 50-50 blend of fossil fuel and the vegetable oil. We saw a huge amount of deposit formation on the nozzle. If we check below the filter before, you see already that the blend itself has an issue with the deposit formation, while the pure components have no malfunctions. So it's always a topic. You see it on the left bottom. We need the efficiency of the system, okay? We need the storage stability of the fuels, and we need the operability of the whole system. And I think all these 3 points have to point it out with the new fuel. And that's why we do this testing here. And yeah. As mentioned before, I would like to focus in this talk a little bit the premium fuels, so what is possible with additive treatment. And first of all, what is a premium fuel? So in Germany, with this BDH, this is a German Association of Manufacturers of Heating Devices, and they make a wish list or a definition what is necessary to be a premium fuel. So first of all, we need a long-term storage stability, high thermal stability, but also some corrosion protection, protection against water take-up, keep clean up, some resistance against microbial contamination. Odor, okay, it's also in. And I think the last point, no ash forming additives, I think that's is also on standard in Germany. That's not a premium-like fuel. But if we go through all these points, most of them, or nearly all of them, can be affected by an additive treatment. And this is what we take a look on the next slides. There are a lot of additives in the market, so I think it's not a problem to find an additive if you want to face one of the effects. So keep the system clean, take in detergent. Do you want an increased storage stability? Take some antioxidant. I think the main challenge is the additive mixture. So you don't want to face just one of these effects, you want to face them all. So the challenge is to find or to define a mixture of additives which are working in the fuel or in the system. And in this case, it's not important that it worked in one fuel, because the fuel itself has a broad range of characteristics or behavior. So you need a good additive mixture which worked in every fuel in best case. So if you want to test all the claimed effects, you need a lot of fuel and test time. Also, I think the most challenge is that if you create a new fuel, you don't have these huge amounts to test everything. So in this case, Tech for Fuels developed an hardware-in-the-loop test. So it's a complete real system without the combustion, and so we can reduce the fuel needed for the test, but also can test all the claimed effects in nearly one test. Before showing you some results of these tests, I would like to give you some background information. So it's a stress test for the evaluation of an additive performance or the fuel itself. So we have an hardware-in-the-loop test principle. So we have the complete heating oil system. We have the filter, the pump, preheater, and the nozzle. And we pump the fuel or the blended fuel through all the fuel leading parts without the combustion in the end. So we have a defined fuel aging. So the light, heat, oxygen, kappa, it's always the same parameters. So we can guarantee in comparable results. We have a periodic fuel analysis in between, and further measurements, so flow rate and so on, which can give or deliver additional data regarding the clean up effect of the fuel. On this slide, I can show you some of the results, or one result of the test rig. So on the x-axis, we see the hours of operation, and on the y-axis, the flow and rep per minute. And we tested here 4 different fuels, 2 different domestic heating oils without additive, and the same domestic heating oil with a performance additive package. We always tested 2 different domestic heating oils with the same additive to be sure that it's not working only in one fuel, the additive package. So I don't want to go too much in detail. I think domestic heating oil 2 showed nearly no problem even without additive treatment. But if we take a look on the domestic heating oil 1, it's a red dotted line. We saw after 200 hours of operation a decrease in flow, which led to a failure of the nozzle, a huge deposit formation. I can show you some pictures afterwards. And after reinstalling, the flow is coming back with a new nozzle. But the point of this slide is that the additive treated blend or fuel doesn't show any significant change in the flow rate. So the additive worked fine here in both domestic heating oils. Here we see the corresponding pictures of the nozzle of the test mentioned before. So the domestic heating oil 1, after 380 hours of operation, have a huge deposit formation on the filter of the nozzle. Then after changing the nozzle, we had another run of 570 hours of operation, and then again the nozzle was blocked with deposit formation, less strong than the first one, and then the last one for the 1,000-hour test time runs only 50 hours before test ended. And if we take a look on the additive treated fuels, so on the bottom left side, domestic heating oil 1, on the right side the domestic heating oil 2, showed no deposits on the nozzle filter in this case. In addition, the periodic analytic also includes the corrosion test. So after 500 and 1,000 hours, the fuel is also investigated analytically, and here we show that the domestic heating oil 1 shows also strong aging and then therefore corrosion on the test strip, and the additive treated blends showed more or less no corrosion behavior. In the last chapter of this presentation, I would like to focus again the oxidation stability. So I talked before about the long-term stability in the glass bottles, and you also takes a long time, 12 or 18 months, before the final analytics are done. So this time is really long. So we define an accelerated aging. So we have some really higher stress parameters. And I would like to focus now on the next slides for this test methods. In order to have a much faster evaluation of the fuels regarding the out-oxidation reaction or resistance against out-oxidation, we find this accelerated aging called Big Oxy here. Has some similarities to the Petro-Oxy test. Maybe some of you knows already about this. So we have really high stress conditions and rapid aging. We can change all the conditions together with the customer. So pressures between 1.2 and 5 bar are possible, temperatures up to 250 degrees centigrade, or different aging periods. It's really flexible, this test, depending on the effect the client or the customer wants to look at. So it gives an initial impression on the long-term behavior of the fuel. So it's not one-to-one the aging in the tank of the customer for sure, but the fuel is aged really hard, and they can have a look on the fuel stability, or if you test the additive performance itself. Since a few years, we're working together with Shell on the investigation of paraffinic fuels according to DIN 15940 and the effect of oxidation stability of these paraffinic fuels. Here we test the Shell GTL fuel and compared it with a domestic heating oil. And the graph we see here is on the x-axis the time in hour, and on the y-axis the normalized pressure of this test. And it's divided into two parts. And the part on the top is the fossil fuels, different domestic heating oils, and the big oxy run, so with the high stress conditions. And we see a fine differentiation of the different domestic heating oils. And also we see in the black dotted lines and the black line, it's the same DHO after 1 year of storage. So it's just in storage under ambient conditions. So it's not enforced aging of the test fluid. And on the bottom part of the graph, we saw the different paraffinic fuels we tested here. So it's two different paraffinic GTL fuels. The black line is a 1 year and 2 year old paraffinic fuel, so it's also under ambient conditions aged. And the red one is a second GTL fuel, which stored just a little bit longer, 5 and 7 years. And the paraffinic fuels itself shows a really good long-term stability compared to the domestic heating oil. And also, if we test the blend between DHO and the paraffinic fuel, it's not shown here, but in our investigations, we showed a really good improvement in the stability of the blend during long term. On this slide, I would like to pick up two of these previously seen paraffinic fuels in the big oxy run. So maybe in addition to the last slide, we have here again the normalized pressure of the big oxy run, and during aging, the oxygen from the atmosphere above the fuel is installed in the fuel itself. So we see a pressure drop during aging, and that's what we have here in the graph again, the normalized pressure and the pressure drop due to the aging during the test. And here we have again in the black line the paraffinic fuel 1 after 2 years of aging. Again, it's an ambient condition, so it's stored in IBC for 2 years. And then the red line is a 7 years old paraffinic fuel. And as you can see here, the pressure drop of the 7 years old GTL is a little bit earlier than the 2 years old paraffinic fuel. But in this test series, we want to check, okay, what is possible after an additive treatment. So we had here again a performance additive, and also the really old paraffinic fuel, 7 years old, has a quite excellent oxidation stability after additive treatment. Again, about 120 hours of operation, there was no pressure drop detectable. So it's a really high resistance against the out-oxidation. Finally, I would like to zoom up before I have to end up with the talk. So the overall goal is the reduction of the greenhouse gas emissions, and therefore we have to introduce some new fuels or new techniques to the market. And I think it's really important that we always focus the whole system. So we have the efficiency of the system, we have the storage stability of the fuel, but also the operability both together. And therefore, advanced fuels have to be fit for purpose, and also have a quite good storage stability, compatibility with the materials have to be tested. And I think I show you with the hardware-in-the-loop principle that we can deliver early impressions what the fuel interactions with the system components or the additive performance will do with the fuels and the system.